In this video, we're going to look at basic trigonometric equations. Recall in previous videos we looked at some of the basic trigonometric equations. These were things like sine of theta equals root 3 over 2, or cosine of theta equals a half. To solve a basic trigonometric equation, the idea is to isolate the trig function, take the inverse of both sides to find the reference angle and the quadrants that the reference angles make sense in. Then we find the solutions in one period of the function, or you can think about one revolution, so between 0 and 2 pi. And then we use that to find the solutions for all of the values, so in any revolution of the unit circle. The main difference between some of what we're doing now and what we did before is instead of just being given the isolated trig function, you are going to have to take those first steps of isolating it and then taking the inverse trig function. So for example, let's find all the solutions of square root of 2 sine theta plus 1 equaling 0, where the solutions are given in radians. So to start this equation, we want to begin by isolating the trig function. So we see that sine of theta is going to equal negative root 2 over 2. Then we're going to take the inverse trig function and find the reference angles. And again, when we're looking at the reference angles, we want all of the quadrants where our sine of theta is going to be a negative value. So here we can see that our reference angle, theta, is going to be pi over 4 in quadrants 3 and quadrants 4, since those are the two places our sine is going to be negative. Okay. So now if we get the actual angle values, pi over 4 in the third quadrant is going to be 5 pi over 4, and pi over 4 in the fourth quadrant is going to be 7 pi over 4. So if we were just asked to find the solutions in the interval from 0 to 2 pi, those would be our solutions. But here we want to find all of the solutions. So now we have to think of all possible coterminal angles with this. So our solutions for this equation are theta equal 5 pi over 4 plus 2n pi, and theta equal 7 pi over 4 plus 2n pi. In this next example, we're going to look at the solutions of 2 times cosine squared of theta minus 1 equaling 0. So here the idea is the same. The main difference is we are now looking at powers of our trig functions. Okay, so to solve, we're still going to do the same thing. The first thing we want to do is isolate the trig function. So isolating our trig function, we see that we end up with a cosine of theta equaling plus or minus the square root of 2 over 2. And so we can separate this into two equations now, cosine of theta equaling the positive value and cosine of theta equaling the negative value. At this point, we're going to do the same thing now that we've isolated the value, our trig value. We want to use the inverse cosine to isolate the angle theta. So looking at our reference angles, we want to find the angles where cosine is positive root 2 over 2, which is going to be 45 degrees in quadrants 1 and 4. And we also want the values where cosine inverse of negative root 2 over 2 equals our theta. And so those are going to be 45 degrees in quadrants 2 and 3, where cosine is negative. So we're getting 45 degrees in all four of the quadrants, which means if we look at our values, it's going to be 45 degrees plus all revolutions of that, 135 degrees, which is the quadrant 2 angle, plus all revolutions of that, and then same thing for quadrants 2 and 3, 3 and 4. But notice in quadrant 3, it's just 180 degrees from the value in quadrant 1, and likewise the value in quadrant 4 is 180 degrees from our quadrant 2 angle. So we can write this as 45 plus 180 degrees times n, and 135 plus 180 degrees times n. And that will include all revolutions of our 45 degree angle in each of the four quadrants. In our next example, we want to solve the equation 4 cosine squared of theta minus 4 cosine theta plus 1 equal to 0, and we want to give the solutions in radians. And so here again, we're taking a step up from the last example. Now we have both powers of our trig function as well as the trig function in the equation. And so here we can think of this as one of our polynomial equations. If we had something like 4x squared minus 4x plus 1, we would think of it as a quadratic and we would try to factor or solve using those methods. Some of your trig equations are going to be the same way. I still want to start by isolating the variable or the trig function, but in some cases isolating that trig function means I'm going to have to factor or rewrite the equation in some way. Okay. So here we can start this one by factoring the equation. So isolating our factors, in this case the factors are both the same, so isolating that to cosine theta minus 1 equals 0, we can move things around and get cosine of theta equal to half. Now we'll take the inverse trig function and find our reference angles. So if theta equals the inverse cosine of a half, theta, our reference angle, is going to be pi over 3 in quadrant 1 and in quadrant 4, since those are where cosine is going to be positive. So looking at our value in quadrant 1, it's just going to be pi over 3, and we want every revolution of that. And then in quadrant 4, we're looking at 5 pi over 3, and we want every revolution of that. So theta will equal pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. So for our last basic trig equation, we want to solve cosine of theta times sine of theta minus 1/2 cosine of theta equaling 0. And we want to give all of the solutions in degrees. So in this case, to do this, because I have more than one trig function, again, just like in the last example, we're going to start by factoring. So I notice there's a cosine in both terms. I can factor that out. So now I have two things multiplied to equal 0, so I'm going to separate this into two separate equations, and again isolate my trig function and take the inverse value. So for the first equation, we're looking at theta equaling the inverse cosine of 0. We want the solutions in degrees, and we know that cosine is going to be 0 at multiples of 90 degrees. So at 90 and 270. So our reference angle is 90 degrees and 270 degrees. For the sine theta equaling a half, we get that theta is the inverse sine of a half, and for those we're looking at 30 and 150 degrees. So again, first and second quadrant where sine is positive. So this gives us all of our values in the first revolution, or one period of the trig functions we're given. We want all of the values, so now we're going to look at all the possible revolutions of these angle values. So for the inverse sine, at 30 degrees, we want every 360 degree revolution of that. And for the 150 degrees, we want every 360 degree revolution of that. For the cosine inverse, notice if I look at 90 and 270, they're exactly 180 degrees apart. So here, I want the 90 degree angle and every 180 degree revolution of that.